How's it going? Who left? Michael? Yeah, he left early for soccer. Yeah. Of a class or school?
No. He's totally messing with it.
You wouldn't. They don't want to say Michael, huh? I'll be listening to the video now. Questions about anything before we get started? Yeah.
In this class, we get to chapters 10 and 11 and just nothing.
In this class, we'll get to 5.
Oh.
Next semester is when we go farther.
This is a 2-semester class.
Well, if you're going to take mathematical statistics, yes. Yeah.
Yes.
Yeah, it's the same one we have class.
Man, now I gotta do it for right there.
Yeah, me too.
Sorry. Same book for both semesters. Same professor for both semesters. So, you know, if you have to take it, you're stuck with me. So, anyway, other questions? No? All right. So last time we talked about some of the beginning properties of probability. Pardon me. So what we need to start building on are ways to start computing some probabilities. So what we're going to do in this next chapter, or this next section, is talk about ways to count ways that events can happen. You probably, if you've seen this in other classes, like for example discrete math, you see this in. Some people see it in pre-calculus classes in high school. We're going to be talking about doing multiplication principle, permutations, and combinations. So you'll see the counting ideas popping up here. And again, this is just ways to enumerate total number of possibilities for, well, again, what we refer to as discrete events. These methods of enumeration don't work for continuous events. We'll talk about how we do continuous probability later. But for now, we'll just talk about how we count these things up. So section 1.3 talks about methods of enumeration. And really, everything as far as methods of enumerations go is based on the single principle of multiplication principle. So let's just write that down first. So, to give you a specific example, say you run an experiment which involves flipping a coin and rolling a 6-sided die at the same time, or one after the other. It really doesn't matter, because if you flip the coin, that's not going to affect how you roll the die. Okay. So, how many different possible outcomes are there if I record both outcomes? So, I want to know what happened on the coin and what happened on the die. How many different possible outcomes are there? 12, okay? So you can do heads with all of them, or tails with all the possibilities for the die, right? Heads in a 1 through 6, or tails with a 1 through 6, right? Notice that there's 2 ways for outcome for the die, or the coin, 6 ways for the outcome of the die, and we need 2 times 6 to give us the 12, right? Which makes sense because for each outcome for the first, whatever it is, either the die or the coin, there is the corresponding number of outcomes for the second piece, right? So that's exactly what the multiplication principle says. Multiplication principle says that if task 1 can be performed in m ways, and task 2 can be performed in n ways, and the total number of ways that task 1 followed by task 2 can be performed is m times n. Some people see this better visually with a tree diagram. I don't typically ever write out tree diagrams. Sometimes the problems in the book will say, use a tree diagram to show this. Some people are just better visual than, well, me. I'm not a very visual person as far as mathematics goes. That's why I'm an algebraist. Lots of symbols. Symbols are good. Symbol pushing. Algebraists are symbol pushers. I'm a good symbol pusher. I'm not good visually. Okay? So if you think about the coin flip followed by die roll. Okay? Coin flip has two possibilities, right? You got heads and tails. Right? And then die roll has 6 possibilities. Same thing down here. This is what I mean by a tree diagram. So each of these would be 1 through 6. I know I'm writing that small. And then each path through the tree, I roll my one way up there. Each path through the tree tells you a possible outcome. So if I start here, flip heads and go roll a 1, that gives me a heads and 1 for one of the possible outcomes, right? Or if I go up to heads and down through 4, and we have heads 4 as another possible outcome, or tails 2, right? So following each of the possible paths from the starting point out to the edge gives you a possible outcome for the experiment. Yes?
For the multiplication principle, do the laws of commutativity and associativity hold too? Like if I roll a die, then flip a coin, and then roll another die, does it the same thing as rolling a die, then rolling a die, then?
Yep. Exactly. Yep. Those would follow the same rules. So each of these paths here, so this would be like heads 1, heads 2, heads 3, and so on. You can actually enumerate them. But you can see the number of possibilities there are just the number of endpoints that you have here. And if you're familiar with the language of trees from graph theory, we think of this as the root where we start, and these would be the leaves where we end. Most of your trees typically are written from top down as opposed to left to right, but it's the same concept. If you like top down, turn your head sideways. Then it's top down. You people actually did it. That was awesome. All right. So, again, if you're a visual kind of person, this tree diagram can help you enumerate the possibilities. Of course, most of the problems that we're going to have thousands or millions of possibilities. You're probably not going to want to draw a tree. Just guessing. Okay? Probably not. All right. So, to go along with the same idea, we want to start trying to come up with different ways to count things that don't require drawing trees necessarily every time. So, just to look at some particular examples, let's look at, well, let's just say I ask you as an example, how many 7-digit telephone numbers are possible? I'm not going to worry about telephone numbers that aren't allowed by the telephone company to start with. We could do that. But for example, you can't start a telephone number with a 0 or a 1 because those are special, right? 0 will get you the operator, 1 will get you the long distance. Okay. But let's not worry about that for the time being. Let's not worry about those special cases. Let's just worry about how you would do this. Okay. So notice the multiplication principle was stated in terms of tasks. So in this case, each task of the telephone number would be pick a digit. Okay? So there's 7 tasks that we would need to do. And I like to do that just by representing those with little dashes. And the number of ways that we could perform each task is to simply put a digit in each of those spots, right? Now again, if I'm not going to worry about non-allowable telephone numbers and just worry about the number of possibilities we have for each slot, how many ways can we pick a digit? 10, right? Because there's 0 through 9, correct? So in each of these slots, then there's 10 ways to do task 1, 10 ways to do task 2, and 3, and 4, and 5, and 6, and 7. Right? Now, if we're going to form this telephone number, we're going to do task 1, then task 2, then task 3, and so on down the line. Multiplication principle says, well, you would multiply each of those to get the total number, right? So we would take each of these and multiply them together and get 7, right? 10 million. Now again, that's a lot more than the actual number of allowable telephone numbers because there are other numbers that aren't allowed to start off a prefix for a telephone. Besides being able to use a 0 or a 1 for the first digit, 411 is taken, can't do that. 555 is taken, can't do that. So you have to do a bunch of special cases to subtract them all. But this is was to give you an illustration of what's going on with the multiplication principle. Does that make sense? Well, I said, don't worry about special cases where you can't actually make a telephone number. All right, but what if I asked you the following? What if I said that how many are possible that have no repeated digits? So all the digits are distinct. Now, same concept again. We have 7 tasks. And we're going to do one after the other. So we're going to multiply. Now, how many ways do we still have to do the first task? 10 still, right? Still 10 ways to do the first task, but once we've used that number in the first slot, are we allowed to use it again? No. So how many ways are there to pick the second digit then? 9, and then 8, 7, 6, 5, 4, right? Goes down by 1 each time? Right? We agree with that? All right. And then whatever that turns out to be, did anybody actually do it? What?
600, 400.
They're just spouting out random numbers now. 6, 4, 8, 12.
604,800.
604,800. Is that what you said? Gotcha.
I guess.
All right. So the reason why I did the second example when I did was it gives us an example of another type of counting idea that actually has a special formula that we could use rather than having to do the multiplication principle. The second example is an example of something that's referred to as a permutation. Okay? So let's think about this in general. We had 7 slots to fill, right? We had 10 objects to choose from, but we weren't going to allow any repetition, right? Okay. So that means in the first spot, there was that 10 possible digits that we could pick, and then we went down 1 by each time, okay? Because we weren't going to repeat any. So in general, if I had n objects to choose from rather than 10, I would have used an n here, right? And then here we would use an n minus 1. And here we would use an n minus 2, and so on down the line. Okay? So, scroll. There we go. For permutations, then, so a permutation of n objects taken r at a time is an arrangement of the r objects. So where no object is repeated and the order of arrangement matters. Oops, I missed arrange. How about arrangement? Sorry. So what we mean is, imagine having a basket filled with, I don't care what it's filled with, how about balls with numbers on them, like water. Okay? You're going to reach in, grab a number, set it out. Reach in, grab a second number, set it out. And so on down the line. If those balls are individually and distinctly numbered, and the order in which you draw them out matters, that's a permutation. Okay, so say I get all of you, or some like 5 of you, and put you all in a line. Okay, well then the order that you're in line matters. Especially if I have a limited number of things you can choose from to, I don't know, eat. Whatever, doesn't matter. Limited number of prizes to get. Okay? Those kind of things. So I would select each of you individually and not select the same person twice, and then arrange you in order. That's a permutation. Okay? So we're interested in counting these. The total number of permutations in this case. Well, let's see. The book uses which notation? That one. Okay. So they use the notation NPR. You might also see PN, R. That means the same thing. This you see on your this comes on your calculator. There's a button on your calculator for this. So think about it first as number of tasks and number of ways to perform each task. So if I think about drawing my slots in again, so we'll have R slots. That's an R. It's an ugly looking R. How many ways can we fill in the first slot, did we just say a minute ago? N, right? We agree? And then the next slot would be n minus 1. Next slot would be n minus 2. And we would multiply each of these until we get to the last slot. Well, let's think about it. Basically, this number here is counting the number of slots, isn't it? But we didn't start counting at 0. We started counting at... we didn't start counting at 1. We started counting at 0. I said it backwards. Started counting at 0, right? So instead of having an n minus r here, you'd have an n minus the quantity, r minus 1. Or it would look like n minus r plus 1 on the end. And you would multiply all these together. All right, well, that's kind of an ugly formula and an ugly way to do it each time. And like I already told you, there's a button on your calculator, so there must be some easier way to do this. And you may have seen it before, you may not have seen it before, but to take this class, you should have seen, well, at least Calc 2 and seen a factorial notation before. So let's think about this in terms of factorial. Remember that n factorial is not being really excited about n. It's not n, right? Okay. What does it mean? It means you start at n, go down by 1, for each factor until you get all the way down to 1, right? You agree with that? Okay. So let's see how that would apply here. Well, notice this is starting at n, and going all the way down to n minus r plus 1. Well, if we kept going, the next term would be what? Be n minus r, and then n minus r minus 1, n minus r minus 2, all the way down to 1, if I did n factorial, correct? That last piece that I just said was on here would start with n minus r and be all the way down to 1. So that tail piece there would be what? It'd be n minus r factorial, and that's exactly what we want to lop off, right? So this would be exactly the same thing. This NPR would be n factorial divided by n minus r factorial. So there's a formula for the NPR, the number of permutations. Does that make sense? Seen it before? Any of you seen it before? Okay. All right, so this gives you a formula where you've got this, and what's important here are two things. Distinct arrangements, okay? All right, so it's distinct arrangement, so there's two words there. So the distinct means that you've got no repetitions, okay? The objects are all different, so you can tell. And then arrangement means order matters. Okay? All right. So it's order matters, repetitions not allowed. So just to write that down to the side. So for permutations, order matters, repetition not allowed. All right. Now, sometimes we'll have distinct arrangements and the order matters, but we'll see that we're allowing repetition, and then we'll have some other formulas that we'll need to worry about. Okay. So what happens now if you do selections of objects where the repetition is not allowed, but you don't care what the order is? Say 5 of us want to go to Taco Bell. Okay? So if I want to pick 5 people to go to Taco Bell, does it really matter the order in which I pick you? Or is just the group of 5 going to go? Group of 5 is going to go, right? So, or if you're dealt a hand of cards, what's the first thing you do if you've played cards? What's the first thing you do when you get the cards dealt to you? You pick them up and then you order them however you want to look at them, right? Right? If you're playing cards, you probably don't let the 4 of clubs next to the 10 of diamonds, next to the queen of hearts, next to the, you usually order them however you want to see them, correct? And I usually put all the suits all together and then put them in numeric order. That's what I do. But it doesn't matter how you got the cards, because usually when you play cards, you pick up the cards and you put them in whatever order you want to look at them in. Right? That's an unordered arrangement to start with. Okay? So that's what we refer to as a combination. Oops. So if n objects taken r at a time I'll just write as a selection of r distinct objects, so no repetitions, where the order of selection is unimportant. All right, so let's think about how we would count these things. Let's do this by example first, and then see if we can figure out what the actual formula is. So let's say that I make up, this is the set of things that I'm going to choose from, A, B, C, D, E. I'm going to choose 3 of them. Okay? Out of the 5, I'm going to choose 3 distinct. Okay? So when we do that, if I choose 3, I would have ABC as a possibility, ABD is a possibility, ABE is a possibility, right? We agree with that? Okay. Then we would also have ACB, ACD, ACE, right? ADB, ADC, ADE, and then AEB, AEC, AED. Yeah, Chris.
I thought you said that order didn't matter.
I'm getting to that. I'm just doing possible selections. That's what I'm doing right now. You're right. For the combination, the order doesn't matter. I'm just doing possible selections right now and seeing what happens. Okay. So what do we have there? We've got 12. Is that right? If I counted it right? Now I got to do this 5 more times, don't I? And I have 60 different possibilities if I'm just writing out the arrangements, which would make sense, correct? Because that's permutations, isn't it? 5 factorial is 120. I would divide by 2 factorial, because that's 5 minus 3 is 2 factorial. 120 divided by 2 is 60. There should be 60 possibilities, right? If we just use the formula. Correct? Well, let's think about how these come in order. So notice that how many, I could do this ABC here. I'm not going to write out the rest of them. This is just how you would do it, right? But there's other arrangements that could involve those same letters, isn't there? For that ABC, we could, if you do the B's, you would also have BAC, and then somewhere along the line you would have BCA, correct? We agree with that? Okay. And then the same thing for the C, you would have CAB or CBA, right? So notice that ABC I circled, the ACB here, and then these all use the same 3 letters, and they're all rearranged, right? So how many different ways are there to rearrange those 3 letters? 6, right? It's 3 factorial, isn't it, right? 3 ways for the first, 2 for the second, 1 for the third. Notice that the other ones occur in those groups of 6 as well. If you did, say, let's say we had BCD. This is another example. That would be BDC, CBD, CDB. Oops. Oh, for heaven's sake. D's and B's, I always try to write the same way. DBC and DCB. Notice with those symbols, BCD, there's 6 ways to rearrange those symbols as well, right? Now, if the order doesn't matter, all 6 of those should be the same selection, right? Using the cards example again, if I give you the 2 of clubs, the 4 of spades, and the 5 of hearts, that's the same as the 5 of hearts, the 2 of spades, and 4 of clubs. I think I said those right. Whatever. I don't want them to be the same cards. Right? The order doesn't matter. Right? So when I do a selection of 3 of them, there's 6 ways to rearrange them and still have the same effect, the same arrangement, or the same selection, I mean. Right? So when we do this original number of permutations here, they occur in groups of 6 that are all going to be identical if we don't worry about the order of selection. Okay? So the number of combinations here, number of combinations or distinct selections, not worrying about order, right, will be 60, right? That was the total number, divided by 6, right? There's 60 total possibilities, but they occur in groups of 6 that'll all be the same. So you would get 10, right? Now let's think about this as part of formulas. where would this, in terms of formula, where would the 60 come from? There was permutations, 5 objects taken 3 at a time, right? Where'd the 6 come from? 3 factorial. Just the arrangements of the 3 objects after they've been selected, correct? Okay? So if we want to do this in general, if we do Ncr, and there's a couple of other notations that you might see. C of Nr looks like the P of Nr. Ncr is typically what you see on your calculator. However, what you typically see written is what's referred to as the binomial coefficient, Nr. I typically say Nchoose-R. The formula is Npr over R factorial. That's where that 60 over 6 idea came from in the example. But Npr, we have a formula for that, right? What was the formula for Npr? Good. So N factorial over N minus R factorial. So I get a formula for my combinations in terms of N and R as well. Is okay? One of the reasons why that this is called the binomial coefficient is because these coefficients pop up when you do expansions of binomials into powers. They come up as the coefficients in that. You may have heard of the binomial theorem. If you haven't, you will at some point. All right. Okay, so let's see if we can do a couple of problems here out of the book and see if we all can make sense of what's going on. So let's look at, first let's just look at 1.3-5 in the book. 1.3-5 says, we're going to ask how many words, how many 4-letter code words can be formed from the letters of HOPE. Now, there's a couple of different questions you might be asking about this because I didn't say anything about restrictions, right? In the actual problem, it's actually 2 parts. Part A says letters can't be repeated, where part B says letters can be repeated. So for part A, if the letters can't be repeated, what are you going to get? Yeah, that's it. 24, and how did you come up with the 24? Yeah, so you can think of it as there's 4 ways to pick the first letter, 3 ways to pick the second, 2 ways to pick the 2 letters from which to pick the third, and 1 for the last one. So that's 4 factorial, or 24. Certainly, if we're making a code word, or the order should be important here, right? If the order is not important, you're just going to get 1. There's only 1 way to select the 4 letters, right? It's not a really interesting code word. All right. We okay with that? How about if letters can be repeated? What are you going to get? And how'd you come up with the 256?
4.
Good. So there's 4 ways to pick a letter each time, right? If you're allowed to repeats, there's 4 ways to do it each time, correct? So you would get 4 to the 4th for 256. Does that make sense? Any questions on that one before I do the next one? All right. Well, let's look at 1.3-6. 1.3-6 is making an ice cream sundae. You know, it's good for around lunchtime. Oops. So they've got 4 different ice cream flavors. It's not really as important what the flavors are as it is that there's 4 different ones. And they have 6 different toppings. And again, not necessarily important as what the toppings are as the fact that there are 6 of them and they're distinct. That's important. All right, so let's go piece by piece here just to see if we can illustrate the different counting methods. So part A says how many Sundays have, one flavor of ice cream and 6 toppings. Not 6 toppings, 3 toppings, sorry. Bless you. Okay, so this is a good illustration of a little bit more complex problem because we need to break this into tasks, and then each task is going to have a certain number of ways to compute the number of possibilities. So the way we can think about breaking this into tasks is to pick the ice cream, then pick the toppings. Okay? Well, picking the ice cream is pretty easy. You're going to pick one ice cream flavor. How many ways are there to do that? 4, right? So for your ice cream flavors, there is just 4. The second part's a little bit more complicated. So this is where you need to think about your different rules for counting things. You're going to pick 3 toppings, and I assume I mean 3 separate or 3 distinct toppings. You're not going to ask for double strawberries. Okay? I'm assuming that. You might want double strawberries. I don't know. Okay? But you're going to pick 3 distinct toppings, which means that repeats aren't allowed, right? So as soon as you think here repeats aren't allowed, you're thinking permutations or combinations, right? At least I am. Okay? You're thinking permutations or combinations. Now, if you're going to put 3 toppings on your sundae, does the order in which you pick the toppings matter? No, not unless you're a 4-year-old. No, it has to be in this order. Okay? Right? It doesn't matter. The order doesn't matter, right? If you're going to pick caramel and M&Ms and nuts, it doesn't matter which order they really go in, unless you're really, really picky. So is that a permutation or a combination? Combination. So we've got 6 items to choose from, and we're choosing 3 of them, correct? Yeah, okay. Which gives you, I think, 80 total. I did my arithmetic correctly. By the way, the NPR and the NCR buttons are on your calculator. If you want me to show you where they are, I can. They're under the math menu and under the PRB menu. The TI-30 is the one you're going to use on the exam P if you're doing that one. Yep, that's the one. And there's the NPR and NCR is on there as well. The tricky part with that is that you have to type in the number first, then go find the symbol, and then type in the second number. So it'll look like number, and then the symbol is NPR, and then it'll be the second number. Unless you've got one of the nicer 84s, then I actually think it puts little subscripts in there, and you type it in the subscript. If you got an older 83 or the TI 30s, then it'll be number, symbol, number. But the newer 84 is actually you put the subscript in there and you fill in the subscript. Just kind of nice. That was kind of a nice advancement for that particular function. Hi, Grace.
How do you do that?
We always type in the 6 first. Everyone okay? All right, so let's look at part B, where we're going to do 1 ice cream and 0 to 6 toppings. Well, the 1 ice cream is still pretty straightforward, right? It's going to be 4 times something. Okay. There's a couple of ways to think about the 0 to 6 toppings. First way to think about it is you could do 0 toppings, or you could do 1 topping, or 2, or 3, or 4, or 5, or 6, right? And then we could do each of those using our formula, right? Our combination formula. So if you thought about it that way, you could make that 6, that would be 6 choose 0 is the number of ways to choose no toppings, correct? 6 choose 1, 6 choose 2, up to 6 choose 6, right? Now notice I said or, correct? I said 6 choose, like I said, choose 0 toppings, or 1, or 2, or 3, and so on down the line. What set operation makes you think, what do you think of when I say the word or? What set operation? You're right. Yeah, that's right. It's union, right? When I do or, that's union, correct? And if I want to count in a union, we add, correct? As long as they're disjoint, right? As long as they're mutually exclusive, as long as they're disjoint, we can add, correct? Well, I can't choose 0 and 1 at the same time, right? It's either or. So if I want to count those, I could add them together and get that answer. Now that's a lot of computation, isn't it? Yes, I think it's a lot of computation, okay? So we can think of that as a different way. How many total toppings are there? 6, right? So let's think about it in terms of going selections again. I get to topping 1. I either want that topping or not. So how many choices do I have? If I get to topping 1, I can either choose it or not. How many choices do I have? 2, right? Get to topping 2. I want it or I don't want it. How many choices? 2. Get to topping 3. 2. Get to topping 4. 2, right? I have 6 ways, I have 6 tasks to complete, right? Task 1, do I want caramel? Task 2, do I want whatever the second one was? Task 3, hot fudge. Task 3 was, do I want marshmallows? Task 4 was, do I want M&M's? 5 nuts, 6 strawberries. Did I get them in the right order? Ooh, okay, cool. Right? Those are the 6 tasks that I had, right? For each of those, I've got 2 ways to do it. Multiplication principle says I do what with all those 2's? Multiplying, because I got to do it for each one, right? So I could also do this as, instead of doing that big long addition, I could do this as 4 times 2 to the 6th. That seemed a little easier, didn't it? Yeah. Okay. Oops. No, that's not 128. That's 256, isn't it? It's 2 to the 8th, which should be 256. A little bit easier, right? there's actually a theorem that says that this is actually a corollary of the binomial theorem that says that 2 to the n is the sum from I equals 0 to n of n choose I, which is what we're doing in those brackets. It's a cool theorem. Okay. I mean, not necessarily the theorem. I'm just saying is the problem okay. All right. Let's see. Let's look at. I want to look at one more or wait till next time? I'll get 3 minutes. I'll wait till next time. All right. Wait till next time to do another one. Then I'll give you a homework assignment next time as well to turn in over 1, 2, and 1, 3. We'll also get into 1, 4 next time. But when I give you homework to turn in next time, it'll just be over 1, 2, and 1, 3. Remember again, if you're looking for practice problems while you're waiting for me to give you an assignment to turn in, all of the odd solutions are on Moodle. So you can look at odd problems in the sections and work through them and see if you're doing them right. Okay. It's not very important. Okay? All right. Have a good one. We'll see you Monday or Wednesday, I mean. Yeah.
Okay, if we weren't doing that, we would add them up.
Yep.
Okay.
Yep, that's right.
Okay, I just wanted to make sure we had everything.
Nope, that was that. Yep, that's right.
Thank
Yep,
you.
you're welcome.